Semigroups and their representations, Lecture 20, Problem Session. Problem 1. Describe explicitly all simple modules over the semigroup PT2 over any field K. Let's recall that PT2 is the semigroup of all partial transformations of the set 1, 2 with two elements. Solution. The semigroup PT2 has a total of 9 elements. We have two elements E and S that form the symmetric group S2. So E is the identity on 1, 2, and S is a transposition of 1 and 2. We have the 0 element, which we denote by Z. That's a unique element in PT2 with empty domain, so of rank 0. We have 4 elements which we denote by tau ij. These are elements of rank 1 with singleton domain I and singleton codomain j. Both I and j are elements in the set 1, 2. And finally we have two elements pi sub I who have rank 1, but the domain consisting of 1 and 2, and then the codomain is the index I of pi sub I. That's an element in 1, 2. The semigroup PT2 has 3 j classes, which are indexed by the rank of the element. If the rank is R, which can be 0, 1, or 2, then the corresponding j class is denoted by j sub R. Note that all j classes are regular, so each simple module has an apex, which is a j class, and this j class must be a regular j class. In our semigroup, all j classes are regular, so they all can be apexes of some simple modules. So let us start by describing all simple modules with apex j0. The corresponding j class, the class of all elements with rank 0, is singleton and just consists of the idempotent Z. So the maximal subgroup of this idempotent is a singleton group, and this group has a unique simple module over any field, namely the trivial module, the field itself, and the action of all elements on this module is trivial. And so the corresponding PT2 module will be the trivial PT2 module. It is one-dimensional, just the field itself, and all elements of PT2 act on this module as the identity element. Next, let us move to the apex j sub 1. This j class has 6 elements, namely the 4 tau ij's and the 2 pi i's. This apex, this j class, has 3 left classes and 2 right classes. The 2 right classes are indexed by the codomain of an element. This codomain might be an element 1 or the element 2. And the 3 left classes are indexed by the domain, and this domain is either 1 or 2, or the whole set 1, 2. So here is the egg box diagram for j sub 1. So the left class L, which corresponds to the domain 1, consists of tau 1, 1 and tau 1, 2. The left class, which corresponds to the domain 2, consists of tau 2, 1 and tau 2, 2. And finally, the left class, which corresponds to the domain 1, 2, consists of pi 1 and pi 2. The right class, which corresponds to the codomain 1, consists of tau 1, 1, tau 2, 1, and pi 1. And the right class, which corresponds to the codomain 2, consists of tau 1, 2, tau 2, 2, and pi 2. Let us take in this class the left cell consisting of tau 1, 1 and tau 1, 2. So here the element tau 1, 1 is an idempotent, it's just the identity on 1. So the H class of this idempotent is a singleton group, as we saw in the egg box diagram. All H classes are singletons. So we have the singleton group, and the singleton group has a unique simple module over any field. That's a trivial module. If we induce it using our left class all the way up to PT2, this trivial module, we get the left cell module corresponding to our left cell. Let us note that this left cell module is isomorphic to the natural PT2 module k to the power 2,
And under this isomorphism, the index I, an element of 1, 2, of the standard basis vector E sub I in k to the power 2 corresponds to the codomain of an element in our left cell. So tau 1, 1 corresponds to E1 and tau 1, 2 corresponds to E2 under this isomorphism. This natural PT2 module k to the power 2 is simple, as it is simple already when we restrict the PT2 action to the action of IS2. The symmetric inverse semigroup IS2 is a subsemigroup of PT2, and the natural representation of IS2 is simple. Therefore, this natural representation is also simple as a PT2 module. And that's an example of our second PT2 module which exists over any field. Finally, let us go to the J-class J sub 2. This J-class contains two elements, E and S, and they form a group. So this J-class has a unique left, unique right, and so unique H cell, and that's a symmetric group S2. So the corresponding maximal subgroup is the symmetric group S2. If the characteristic of our field is different from 2, then the group S2 has two different simple modules, both one-dimensional. We have the trivial module on which both E and S act as the identity, and we have the sign module on which E acts as the identity and S acts as -1. Taking these two modules and declaring that all elements of PT2 outside S2 act on them as 0, we get two simple PT2 modules. If the characteristic of our field is equal to 2, then the group S2 has one simple module, and that's the trivial module. Taking this trivial module and declaring that all elements of PT2 outside S2 act as 0, we get one simple PT2 module. So, if the characteristic of a field is different from 2, PT2 has four simple modules, 3 of dimension 1 and 1 of dimension 2. If the characteristic of the field is equal to 2, then PT2 has 3 simple modules, 2 of dimension 1 and 1 of dimension 2. And this completes problem 1. Problem 2. Show that restriction from Ptn to ISN sends simple left Ptn modules to simple ISN modules over the field of complex numbers, and hence gives rise to a bijection between the set of the isomorphism classes of simple Ptn modules and the set of the isomorphism classes of simple ISN modules. Solution. Let us recall that in general ISN is a submonoid of Ptn. Both monoids are regular, and the J classes of both monoids are indexed by the same thing. In fact, they are indexed by the rank of the element in the corresponding J class, and this rank, k, ranges between 0 and n. Let us tweak some k between 0 and a, and let us consider the corresponding J class J sub k of Ptn. Inside the J class J sub k, the left classes are indexed by equivalence relations with k equivalence classes on subsets of n underlined. This corresponds to the kernel of the element which the corresponding left class contains. So note that we work here with partially defined map, so they are defined on some subset of n underlined, and then the kernel of the corresponding map is an equivalence relation on this subset. And the right classes inside J sub k are indexed by k element subsets of n underlined, and this naturally corresponds to the image of the element inside J sub k. Let us consider the left class capital L, which contains the identity transformation epsilon sub k on the subset k underlined. That's a subset 1, 2, 3, and so on, all the way up to k. Then each element of this class has rank k and domain k underlined with exactly k elements. This means that all elements of L must be bijective on their domain. In other words, all elements of L belong to ISN. So we have now found a left class inside J sub k, which is at the same time a left class in Ptn and a left class of ISN. So these two semigroups have a common L class inside J sub k. The maximal subgroup, that's this maximal subgroup which corresponds to our idempotent epsilon sub k, is isomorphic, or depending on convention is even equal to the symmetric group Sk on k elements. And this means that if we linearize this left class, so this linearization is at the same time a bimodule where the left action is of Ptn and the right action is of Sk, and similarly the left action is ISN and the right action is Sk. So this linearization of this left class, if we consider it as an element of Ptn, it will be Ptn Sk bimodule, or if we consider it as an element of ISN, we get it as an ISN Sk bimodule. And of course the second structure is obtained from the first Y by restriction from Ptn to ISN. Since ISN is an inverse semigroup, we know that for any simple Sk module M, the corresponding induced module, so when we tensor over Sk, our module M with the linearization of our left class, so this tensor product is a simple ISN module because ISN is inverse. But then Ptn is greater, then ISN is bigger, but this means that the corresponding module for Ptn must also be simple. And from our theorem on classification of simple modules over finite monoids, we have that all simple ISN modules and all simple Ptn modules with apex J sub k are of this form. And therefore, simple modules for these two semigroups are actually the same. So this implies all required claims and completes the solution to problem 2. Problem 3. Show that for all n greater than 1, the algebra C Ptn is not semi-simple. So the complex semigroup algebra of Ptn is not semi-simple for n greater than 1. And construct explicitly some module over Pt2 over the complex numbers that is not semi-simple. Solution. The complex semigroup algebra of ISN is a subalgebra of the complex semigroup algebra of Ptn. That's because ISN is a submonoid of Ptn. And from the previous problem, we know that these two algebras have the same simple modules. The simple modules are the same, just we have the structure as ISN module or as Ptn module. We also know that the complex semigroup algebra of ISN is a semi-simple algebra because ISN is an inverse semigroup, and so its complex semigroup algebra is semi-simple. We also know that if we have a finite dimensional algebra over the complex numbers, this algebra is semi-simple if and only if the dimension of this algebra is equal to the sum of the squares of the dimensions of its simple modules. So this corresponds to the fact that the only simple finite dimensional complex algebras are the matrix algebra. And each matrix algebra, the dimension of the matrix algebra is equal to the square of the dimension of its simple module. Okay, so now if n is greater than 1, then we know for sure that Ptn has more elements than ISN. We have an element in Ptn which is not in ISN. We take all elements of 1, 2, and so on n and send them to 1. That's an element in Ptn, it's not in ISN. Therefore, the dimension of the semigroup algebra of Ptn is strictly greater than the dimension of the semigroup algebra of ISN. So here we need that n is greater than 1. Let V1, V2, and so on Vm be a completed irredundant list of simple Ptn modules. Then, by the previous problem, the same list is a completed and irredundant list of simple ISN modules for the restricted structure. Therefore, the cardinality of Ptn, which is strictly greater than the cardinality of ISN, but the semigroup algebra of ISN is semi-simple. So the cardinality of ISN is equal to the sum of the squares of the dimensions of our VIs. But then we see that the dimension of the semigroup algebra of PTN is strictly greater than this sum of the squares of the dimensions of the simple modules. And so we can deduce that the semigroup algebra of PTN is not semi-simple. And since we know that we have an algebra which is not semi-simple, a very obvious example of a non-semi-simple module is a regular module. An algebra is semi-simple if and only if its regular module is semi-simple. So we have a general example that if we take the left regular module over CPTN, we will get a non-semi-simple module. Here is a more concrete example for the very particular semigroup PT2. So PT2 has 9 elements, but we will construct an example of a 3-dimensional non-semi-simple module. So we construct this module as a dual of a right PT2 module. Consider the right class in PT2, denoted by R, which consists of all elements with codomain 1. So we have exactly 3 such elements. Namely, we have the element pi1, which sends both 1 and 2 to 1. We have the element tau1, 1, it has domain 1 and sends this domain to 1. And we have the element tau2, 1. It has domain 2 and sends this 2 to 1. If we linearize this right class R, this has a natural structure of a right module over PT2, which is given by multiplication on the right. So if we multiply an element and we go outside R, then by definition we get zeros. That's how the right module structure on CR is defined. We also know from the previous problems that PT2 has 4 simple modules over the complex numbers, 3 of dimension 1 and 1 of dimension 2. Also, pi1 is an idempotent with a singleton H class, and if we denote by V the trivial module for the corresponding trivial subgroup, let's denote the trivial subgroup by G, then the linearization of our right class R coincides with V tensor over our group G, and then the right class module C of R. So in particular, since C of R coincides with an induced simple module, it has, by our general theory, a simple top. And a module with simple top is automatically indecomposable. But this module cannot be simple. It has dimension 3, and we just said that all simples have dimension 1 or 2. So C of R is a 3-dimensional indecomposable right PT2 module which is not simple. We can dualize it and get a 3-dimensional indecomposable left PT2 module which is not simple. So in this dualization, of course, we have the natural basis, the dual of the natural basis in C of R. So it consists of the duals of the elements pi1, tau1, 1 and tau2, 1. And the matrices of the action of the elements of PT2 in this dual basis are just transpose of the corresponding matrices of the action of those elements on C of R. And this completes problem 3. Problem 4. Let V be the natural S3 module C to the power 3. Then V is at the same time also the natural IS3 module. Determine the dimensions of the centralizers of the S3 and of the IS3 actions on the second tensor power of V. Solution. Let E1, E2 and E3 be the standard basis of V. Let us denote by Vij the elements EI tensor Ej, where I and J are elements in the set 1, 2, 3. Then these Vij's form a basis of V to the tensor power 2. That's a module of dimension 3 times 3, which is 9. Since the action of S3 just permutes the Vij's, we can consider the orbits of the action of S3 on these basis elements and this will give us some decomposition of our module into a direct sum of submodules. We have two orbits. We have the diagonal orbit, which consists of v11, v22, and v33. Let us denote by d its linearization, so the subspace spanned by these elements. This is obviously a submodule of v to the tensor power 2, and it's obviously isomorphic to the original v. And then we have the orbit consisting of all remaining elements, v12, v21, v13, v31, and v23, v32. And this is an orbit from any element we can get to any other element. And the stabilizer of each element is trivial, which means that that's a regular orbit. It has 6 elements, as many as the group S3 itself. Now let's recall what are the simple S3 modules. The group S3 has 3 simple modules over the complex numbers. Namely, we have the trivial module, the Specht module for the partition 3. It has dimension 1. We also have the sine module, that's a Specht module for the partition 1, 1, 1. It has dimension 1. And we have the two-dimensional simple module, that's a Specht module for the partition 2, 1. And that's the non-trivial summand of the natural module. So the natural S3 module V decomposes as a trivial module plus the two-dimensional simple. So the Specht for 3 plus the Specht for 2, 1. We also know that the multiplicity of any simple module in the regular module equals the dimension of the original simple module. Consequently, we already determined that v to the tensor power 2 is a direct sum of the regular module and the natural module. This means that it splits as the direct sum of the sine module with multiplicity 1. It's a part of the regular part. Then we have the trivial module with multiplicity 2, one from the regular part and one from the diagonal part. And we have the Specht module for 2, 1 with multiplicity 3, twice from the regular part and once from the diagonal part. Next, let us note that by Schur's lemma, there are no homomorphisms between non-isomorphic simple modules. Moreover, from the same Schur's lemma, given any simple module x, the endomorphism algebra of x plus and so on k times is exactly the algebra of all k times k matrices with complex entries. And this algebra has dimension k to the power 2. Consequently, the endomorphism algebra of our v to the tensor power 2 can be computed as follows. The module v to the tensor power 2 is a sum of simples where the sine module has multiplicity 1, the trivial multiplicity 2, and the two-dimensional Specht has multiplicity 3. So the dimension of the endomorphism algebra is 1 squared plus 2 squared plus 3 squared, which is 14. So as the first part of the problem, the dimension of the endomorphism algebra of v to the tensor power 2 as an S3 module is 14. Let us now determine it for the IS3 structure. To start with, let us note that our original module V is actually simple as an IS3 module. So the semigroup IS3 has 4 two-sided cells, namely J0, J1, J2, and J3. So the index is the rank of the element. And the semigroup IS3 has 7 simple modules over the complex numbers, namely, we have the trivial module L sub empty set. So the empty set is a partition of 0. It has dimension 1 and its apex is J sub 0. Then for the apex J sub 1, we have the unique simple module L sub 1. 1 is a partition of 1, and it has dimension 3. That's our natural module. For the apex J sub 2, we have two simples, L sub 2 and L sub 1, 1. 2 and 1, 1 are partitions of 2, and both these modules have dimension 3. And finally, for the apex J sub 3, we have 3 simple modules, L sub 3, L sub 2, 1 and L sub 1, 1, 1. So 3, 2, 1 and 1, 1, 1 are partitions of 3. And these have dimensions 1, 2, and 1 respectively. So our natural module is L sub 1, and also these last modules L3, L2, 1 and L1, 1, 1 are in fact simple S3 modules. The corresponding Specht modules S3, S2, 1 and S1, 1, 1, where the action of everything outside S3 in IS3 is 0. Now, let's look at the module L sub the empty set. It has the apex J sub 0, and this apex annihilates the starting module L sub 1. So it annihilates any tensor power of L sub 1, which means that L sub the empty set is not a summand of any tensor power of V, in particular of V to the tensor power 2. So we can forget about this simple module. Next, let us look at our diagonal subspace D, which is spanned by V11, V22, and V33. This is, of course, also an IS3 module. It's a copy of V. So this is our original module V, which is now simple. So this gives us a copy of L sub 1 inside the second tensor power of V. And finally, we have the subspace R, which is the span of the Vij's with I different from J. This is also IS3 invariant. So let us determine how this decomposes as an IS3 module. Consider the identity epsilon 1 on the element 1. That's an idempotent of rank 1 in IS3, and so it belongs to the J class J sub 1. The only Vij which epsilon 1 doesn't kill is V11. So if I is different from J, epsilon 1 must kill Vij. And this means that the corresponding simple module L sub 1, which is a simple which corresponds to epsilon 1, cannot be a summand of R. Next, let us consider epsilon 1, 2, which is the identity on the subset 1, 2. That's an idempotent of rank 2, and it belongs to J sub 2. If we take a simple module with apex J sub 2, then the element epsilon 1, 2 has on this simple rank 1, regardless whether this is L sub 2 simple or L sub 1, 1 simple. Inside our regular orbit R, the element epsilon 1, 2 acts as the identity on V12 and V21 and kills all the remaining Vij's. This means that our R must contain two summands with apex J sub 2. At the moment we don't know which ones. But each IS3 simple with apex J sub 2 has dimension 3, and R has dimension 6. This means that R is a direct sum of these two simples. Nothing else can be there. We also know that as an S3 module, R has simple summands that appear with odd multiplicity, in fact with multiplicity 1. But this means that R cannot be a direct sum of two isomorphic simples. So it must be a direct sum of two non-isomorphic simples, but we only have two simples with apex J sub 2. This means that R is a direct sum of L sub 2 and L sub 1, 1. Adding everything up, we get that V to the tensor power 2 decomposes as L sub 1 plus L sub 2 plus L sub 1, 1. So our V to the tensor power 2 is a direct sum of three pairwise non-isomorphic simple modules as an IS3 module, and by Schur's lemma, the endomorphism algebra of V to the tensor power 2 as an IS3 module has dimension 1 squared plus 1 squared plus 1 squared, which is 3. And now we see how 3 is different, is significantly smaller than the dimension 14, which we got for the S3 structure. That's very interesting to compare. Additional problems and questions at the end. Problem question 1. Decompose the second tensor power of the natural P3 module into a direct sum of indecomposables. Problem question 2. What can one say about a monoid S
if one knows that the trivial S module is projective. Problem question 3. Construct explicitly all simple modules over any field for the monoid of all Boolean 3 times 3 matrices. Problem question 4. Construct explicitly all simple modules over any field for the monoid PT3. And problem question 5. Determine the dimensions of the centralizers of the S3 and IS3 actions on V to the tensor power 3, where V is the natural module. Thank you very much. This was the last lecture of this course.